All right, welcome back to Mr. PL's for Calculus. This is Unit 4, Day 11, and we're going to be talking about linearization approximation to find an approximation of a value of a function. Basically, what you're doing is you're using a tangent line for some other point, and then you're going to use that tangent line to make a guess as to about what the answer would be for some sort of number that might be a hard-to-predict number. All right, now this is the formula for linearization approximation. I know it looks kind of fancy. It looks like it's really tough, but it really isn't. F prime of A, well, that just means the slope. That is the slope at a given point. And then if you look at this, this really is the point-slope form. If you know the point-slope form formula right here, if you just take the given y and you move it to the other side, that's literally all this is. It's just F of A, which happens to be the height at whatever x you're looking at. So that's the height of the point. And then you're adding it to the slope at that place times x minus that given x. And that's all this really is. Now, what you're doing is, like I said a second ago, is you're using the tangent line at a point close to the one you're trying to find, and then you're going to use that tangent line to predict about what your point would be. And I'll explain that a little bit better on the next page. It says, example number 1, find the equation of the tangent line for this. Okay, pretty easy question to start off with. Find the equation of a tangent line, you need to use your point-slope form. So we already know that x is 2, but what we don't know is the y. So we need to know the point and a slope. So if we know the x, you can plug it in here to find the y. Now we have the point, pretty easy. The next thing you need to do is you need to find the slope of that tangent line. And then that you would use your simple power rule. X cubed becomes 3x squared. Plug in your 2 and you get a slope of 12. And there's your tangent line equation, something you've probably been doing since the very beginning. All right, now use your linearization approximation to approximate what 2.1 would be. Now, slightly different here. So 2.1, I could put 2.1 into this equation and solve for y and get a different point. That is technically one way of doing it, but you're not going to do that when the questions get a little bit more complex. The whole point of this is I'm going to use this tangent line, which is the tangent line of this equation at 2, and I'm going to use this equation, this linear line, and I'm going to approximate 2.1 using this equation. Now, will that be exactly where it is? No, actually, I know it won't be exactly where it is, but it's going to be very, very, very close. So if I plug 2.1 in for x right here, and you can see I did the math, 0.1 times 2.1, and then add that to the 8, and you get 9.2. So it's going to be about 9.2 at 2.1, which is slightly higher. That makes sense, because x cubed goes up, so it should be increasing. So it should be increasing, so it's a little bit higher than 8, which is what it was at 2. All right, I thought I had okay, I get to it here. All right, so essentially what you're doing, since I'll draw it here, so essentially what you're doing is if you're taking x cubed, which you know looks like this, and we're putting a tangent line at 2, which is right here, let's say this is 2. Okay, this is our tangent line. We're going to use this line to predict what the height would be at 2.1. 2.1 is right here. Now, 2.1 would be about this height. So it's a little bit higher than 8. This is a height of 8. So you're using this tangent line to predict 2.1. Now, is it going to be exactly on this curve? No, it's not going to be exactly on this curve. It's going to be on this line. And we're just using this line to predict any point using that same tangent line. Now, it's very close. What I'm trying to say here, I guess, is if you made a tangent line to 2.1, the tangent line isn't going to be much different. It's going to be almost the exact same, because as you know, in order for it to be differentiable, the slope can't change that much. So if I use the tangent line to 2.1, will it be a little bit more accurate? Sure. Will it be much closer? I mean, it won't be that much different, I guess is what I'm trying to say. It's because the slope hasn't changed that much from 2 to 2.1. So what we're really doing is we're making an approximation by making it easier on ourselves by using the slope at 2 to make it easier to approximate at 2.1. All right, so here's what we're going to do with this equation. So now we have a new function, and I would always change this because you're going to have to differentiate it. Always change this to rational, get rid of that radical, so I can differentiate, and that's where I get the slope. I always find the point first, personally. Sometimes they give you the point. It just kind of depends on the question. Here they didn't give us the point. They told us that x equals 0. Plug 0 in here, and you get the height of 1. So we now know 0, 1. That's the easy part. Just plug f as 0. Plug it in. Find the height at 0. And there you have your point, and then you have to find the slope. So then you find the actual slope at 0 by the slope is f prime of 0. Since the derivative, that's what a derivative is. It's at that instant what the rate of change would be. So I plug it in, find that the slope happens to be 1/2. Here's my point slope form, which is my linearization. Basically, if I take this one and move it to the other side. And then once I have the equation for linearization, which means that's really the tangent line of the line that's close to it, that's essentially what that means, and then plug 0.02 in and you get an answer of 1.01. Now, let's talk about over and under estimates next. We're going to use the second derivative, and I've got two little diagrams that I drew that I thought would kind of help you understand why it does what it does. The second derivative, if it's concave up, and I just drew a graph right here. This is my concave up, this is my concave down. The reason why it's concave up is because it's always increasing. The rate of change, the tangent line from left to right is always getting larger. And then this one, if you slid the tangent line from left to right, the tangent line is always getting less. That's what makes this one concave down. So that's the second derivative. Second derivative is concave up and concave down. Now, why is it an over or under estimate? Now, I just chose this random value of a. I don't know, whatever this x value is, doesn't really matter. I drew a tangent line here and I drew a tangent line here. And what you'll notice is if you use this tangent line to make a prediction of any value along the, you could make a prediction at B or C. It doesn't matter. That and that height, if you get that answer or that answer, those are both going to be underestimates. They are both under where it should be. B is under where it should be. C is under where it should be. Then over here, if I do the exact same thing, I put B and C right here. B is going to predict using the tangent line right here. That is an overestimate. So that is over what it's supposed to be. This is going to be underestimate. These are both going to be overestimates. That's above what it's supposed to be. That's where it's supposed to be. This is what my tangent line is going to predict. So anytime it's concave down, that tangent line, no matter where you put that tangent line, I put it at A, but I could have put it anywhere along this x-axis, that entire tangent line is going to be above the entire graph. And if it's concave up, it's going to be entirely below the graph. Now, I'll be honest, I don't have this memorized. I always think about these pictures every time I answer one of these questions. This is always what's running through my brain. Well, if it's concave up, what would that look like? I think of this very basic quadratic equation. Oh, that means the tangent line would have to be under it, so therefore it's an underestimate. Or if it's concave down, that would be like negative x squared. This is what always goes through my mind whenever I'm thinking about this question, because otherwise, if you try to memorize too much in this class, you're going to get overwhelmed. You want to try to make as much of it into logical reasoning as you possibly can. All right, so let's do example number 2. This is just a continuation of the last question. We had the first derivative already. So if we find the second derivative, we end up getting this. If we plug in 0.02 into that second derivative, the whole point of this is to determine if the second derivative is positive or negative. Well, it's going to end up being negative because a negative divided by a positive is a negative. If it's a negative, we know it's like a negative x squared. The tangent line is always going to be above it. So that's going to be an overestimate. Anything on that tangent line is over what it was supposed to be. Once again, use that logical reasoning and then it just kind of makes sense. Anytime the second derivative is negative, you know your tangent line is going to be an overestimate. All right, example number 3. Starting from the beginning, it tells us that the function f of x is cosine of x. Well, we're going to use our point slope form again. So the first thing I do is find the point. Plug this in for x and solve, and you get 0. So there's where I got the point from. Then you need to find the slope, which would be the derivative of cosine of x, which is right there. Plug pi over 2 in. There's our slope. So now we have our tangent line. So I go from here to over here. Here's my tangent line equation, which is the linearization approximation equation. Basically, it is. All you have to do is put that 0 on the other side, which honestly doesn't change anything. Plug in 1.75. I use the calculator for this part, and there's your answer. Now, the question now becomes, is this negative answer an over or underestimate? Well, that's where I'm going to use the second derivative. So I'm going to go back over here on the left-hand side. I'm going to find the second derivative of negative sine of x, which happens to be negative cosine of x, because derivative of sine of x is cosine of x, and it was already a negative. Now, I plug in 1.75, and this is where, once again, I'm just going to think about this. 1.75 is more than pi over 2. So we know we're dealing with something in this second quadrant. And if it's in the second quadrant, the cosine would have to be a negative. And a negative times another negative is going to be a positive. And if it's positive, if the second derivative is positive, we know we're talking about something that is concave up. That tangent line is always going to be underneath of it. No matter where you put that tangent line, where you put it here or here or here, all of those tangent lines will always be underneath the actual function. All right, one more example. Same steps basically for this question. Find the point first. Plug in your a value into here. I know this is worded a little bit differently because it says find a linear approximation of this, but that's the same thing as just finding f of 3.2. Just add 0.2 to whatever the a value was. It looks different, but honestly, don't let that throw you off. It's just the same as saying this. So we're going to use the equation at 3 to solve for what we think it is approximately at 3.2. So we found the point. Next thing we need to do is find the slope. Pretty easy question here. To differentiate this, plug in your 3, and you get 23. That's going to give you this equation. I went straight to the L of x because honestly, it's a step you can actually skip. You don't need to move the minus 6 to the other side of point slope form. It's just kind of easier this way. You always know that y minus y sub 1, whatever this is, just put that on the other side. It's pretty easy. 6 plus the slope times, we have x minus the given x, of course. Simplify that down by plugging in 3.2 and you get your answer. Now the second part of this question, is this an over or underestimate? Well, our second derivative will tell us that. So if I differentiate this again, I get 6x. Right? And if I plug in 3 into that, I don't really care what the answer is. It's going to be, I don't know, about 20, give or take. It doesn't really matter. It's going to be a positive answer. And if it's a positive answer, we're talking about a derivative that happens to be concave up. And if it's concave up, then we know it's going to be an underestimate. Once again, this is what always goes through my brain. Don't feel, you can add little illustrations, even though the reader won't really know exactly, well, they probably will know exactly what this is, but this isn't required. But I always suggest, doing things like this, things that make sense to you that help you remember this is an underestimate. You can always jot those down. You're not going to lose credit, obviously, for this. Yes, you can, on the AP exam, lose credit if you do math that's incorrect. Even if you get the correct answer, if your math's incorrect and you have something that's wrong in the middle, you can lose points. So I don't want to give you the misconception there. Yeah, but drawing little diagrams, I mean, if you think it possibly could lose you points, just erase it. But either way, it helps you not have to remember so much information. Thanks again for watching, and I will see you on the next video, and I hope this helped.